Hello! We are going to, in this video, talk about section 2.6, rational functions and graphs. So rational functions, just to give you an idea of what they are, is functions that you see kind of in fraction form where you have a polynomial on top and on bottom. So that's what rational functions are. You will see typically the asymptotes in the at least on the parent function, the asymptotes on the x and y axis. Sometimes that can be a little bit different. We're going to talk about that, but most of the time you are going to see it like in the parent function for a rational function, which is this one that you're seeing right here, 1 over x. The asymptotes are x and y axis, and then sometimes they can shift and be different places. So I do have a bit of a miswrite on this. I don't want to have to rewrite the whole page of notes just for this one word. But so this says, describe the transformation, that's what we should have here, from that parent function for these two problems. And we're just going to kind of run through how I would see that, okay? The first one's a lot more simple because all we have compared to that parent function is the top number is 2. And on the bottom, they've added a number 3. And so what I want you guys to remember from our transformations unit is when you have a value that you add or subtract directly to x, like here, originally x was the only thing on the bottom, and they added 3 to that, then that shows that there was a horizontal shift. And then the other thing that I see is as this thing was multiplied by a 2. You can see that maybe a little bit easier if you rewrite it in a slightly different format. If we rewrote this as 2 times 1 over x plus 3, that's the same thing. But what you're seeing there is this is a vertical stretch of 2, or say vertical dilation. We like that word as well. So I'm going to say that the transformation was a vertical, we'll say dilation because that's a good word. It works for everything. Dilation of 2. And then we can also say because that number was added in the denominator with that x, it wasn't added off to the side. It was added to the x value. That means that there was a shift that was horizontal. We're going to say this was to the left 3. Okay, you can say horizontal, but when you say left, it really implies the horizontalness of it. So I'm good with that. All right, now part B is going to be a little bit more tricky because there's a lot more going on here. Originally, in this f of x function, the only thing in the numerator was a 1. It was a constant. It was not a whole expression. So what we're going to do to try to see exactly what's going on is we're actually going to have to use some long division to clean this up. We're going to say x minus 2, and we're going to divide that into the 3x minus 7. So remember long division, we take the leading terms and work on dividing those. We think x times what gives me 3x? Well, that would be 3. 3 times x is 3x. 3 times a negative 2 is a negative 6. And then we would subtract these. The 3x's would cancel. Negative 7 minus a negative 6 is actually a negative 1. So what I know about this is I could rewrite the function as 3. Let's see, this is h. We can write this as 3 plus a negative 1 over x minus 2. Remember that remainder thing? This guy was your remainder. Okay, so to write that as a polynomial, I can take that and put it over your divisor. All right, so what we're going to do here is I'm going to rearrange it one more time just so that it makes maybe a little bit more sense. We have this negative 1 over x minus 2, and then this 3 is separately added. So it may become more apparent here, but that negative is going to reflect this across the x-axis. Okay, the 2 on the bottom is a shift right 2. And then the 3 that's added over here is actually a shift up 3. So we're going to say and up 3. We can kind of put them both at the same time is fine with me. Okay, so that's that one. If you see that situation happen, It's a little less obvious exactly what's going on, so you do have to use some long division to kind of work through that. Okay, cool. Let's talk about what holes are. Yeah, a hole in a graph, we've talked about them briefly before, but here's your kind of more formal definition, if you will. It says a hole is just going to be a missing point. And it's going to be a missing point from a graph that was otherwise continuous. Like it was going and going and going, and then it has a little tiny hole where it just like blips out and misses. Okay. Okay. So if we call the point AC, right? A hole at x equals a, AC. That's that point. So C would be the y coordinate. So you can talk about it this way, as if you were looking at a graph and it was coming like from the left-hand side. That's what you're seeing here at this limit. Let me zoom in a little bit more because I think you'll see those a little bit better. So if you see this limit as x approaches a, and that negative afterwards means a from the left side. As it approaches from the left side, your graph is approaching this y value. As well, when it approaches from the right side, it should also be approaching that same value. And what we are able to do is then say, well, if it's approaching that same value from both the left and the right, then the function is just approaching that no matter what. And so we can say, we don't even have to distinguish if it's from the left side or the right side, because those are going to match if it's a true whole like that. Okay, so there are some times where there's just like a hole, but the point gets replaced somewhere else. So that's kind of what you're seeing down here. They said if f is defined at the hole and there is a value for f at that number, okay, then you just know that your limit is not going to match that same thing, okay? That c value is not going to match what f of a really would be. And that's just because sometimes that hole can just be displaced. That little point can be moved to a different location instead of being part of the function. But that's not as common. Most of the stuff we're going to deal with, it's going to just completely erase that hole. Okay, let's look at example 2 and see if we can find holes and asymptotes. Here's zoom out a little bit. I did add as an extra little thing on here because you're going to see some stuff on your assignment that asks you to use limit notation and some that really don't say whether you do or not. We're going to use limit notation on this one, but we may not always, okay? Because, again, it's easier not to when you're writing stuff like this. But if they ask us to write limit notation, we need to be able to do that. So, okay, we're going to do one of these at a time. Example 2, find holes and asymptotes. And we're just going to start off here with these two. I'll move it over when it's time to do C. All right, y'all. Here we go. We have function f of x, and that is equal to x minus 2 squared over x minus 2 to the third. There is no need for you to multiply all that out. You might be like, oh, we should use Pascal's triangle. No, you don't need to. On this one, honestly, the easiest thing is to kind of maybe expand this out just so you can see exactly what's going on. Okay, this is a lot of x minus 2's. But what I want you to think about with fractions like this is you will end up having stuff that cancels. So if you look here, x minus 2 and x minus 2 are going to cancel. X minus 2 and x minus 2 is going to cancel. So what we end up with is a 1 in the numerator over x minus 2. And that is really essentially the same thing. Now, usually when we see these things cancel like that, that's where it implies that there's going to be a hole. Okay, so I would have thought, oh, there's a hole at x equals 2 at that 0. However, because there is a denominator over here that does not get canceled out, this actually indicates there's an asymptote, and the asymptote kind of overrules the hole. So although it looks like we have holes because things are canceling, this is indicating that asymptote down here, and that is going to override that. Okay, so I'm going to say we're going to have an asymptote at this shows a vertical asymptote. Oh my gosh, I can't spell. asymptote. Okay, pretend I can spell. All right, so anyways, we're going to use that to help us find the vertical asymptote. There should also be a horizontal one. Remember how we said like you're typically going to have horizontal asymptotes at like the, or you'll have asymptotes on the X and Y axis unless there's like a shift that happens. Well, this is kind of showing you that there's been a horizontal shift to the right too. So that can show you where that asymptote is, but the horizontal asymptote is still going to be where it always was. It's going to be on that x-axis. You can also show that if you look at a graph. Let me get a calculator real quick. So if we do look at a graph, I need to erase what's on here and let's type this one in. They have brightness on these. People always turn them up. Okay. So if we type in what you're seeing here, just the 1 over x minus 2 like that. We'll say 1 divided by x minus 2. Okay, so you can see I've typed that in. I know there's a glare, so I'm sorry. But yeah, we've got that. Now, if I were to actually go look at the graph, you guys are going to see something like this. So there is a horizontal asymptote still here on your x-axis, but the vertical one is not on the y anymore. The vertical asymptote is here at x equals 2. And you can see that from a graph, but you can also do it just by solving out this denominator, okay? So I'm going to say we've got a horizontal asymptote at y equals 0. No. Yes, y equals 0. And we're going to say, we're going to say our vertical asymptote is at x equals positive 2. Like I say, you can just solve that denominator for 0, and it'll give it to you. All right, now we have to use limit notation, right? There's not going to be any holes here because the asymptote kind of overrode what the holes would have been. But let's write limit notation for each of these real quick, okay? All right, so on the horizontal asymptote, what I would say is that my limit as x approaches negative infinity, okay? So again, look here. As it goes towards negative infinity, what is my y approaching? It's approaching 0. So f x equals 0. Whereas my limit as x approaches positive infinity, right, as it goes to the right for forever, let's look at this again. As it goes to the right for forever, the y is also approaching 0. So that's my limit there, okay? So that's the limit for the horizontal asymptote. For my vertical asymptote, it's going to be kind of similar, but we're going to say my limit as x approaches this value, 2. So as we approach 2, and we want to be kind of specific that as we approach that value of 2 from the left side, okay, so look, if I approach from the left side or if I approach from the right side, it's going to be a little bit different. So if I were to draw, don't do this at home, y'all. This is a dry erase marker. If I were to draw that little asymptote that I'm talking about in here, look about what's happening when you approach this from the left side. You see how the graph is going down for forever? Well, that means as it's approaching from the left, my function is getting closer and closer to negative infinity because it's going down for forever. Whereas if I approach this from the right side, it's actually going up for forever. So I'm going to say over here, limit as x approaches 2 from the right side is actually different. And that's okay. That happens. In calculus, you'll do a little bit more with that. But for right now, we're just going to leave that the way it is. Okay? All right. That was example A. Let's look at example B. All right, example B, we got a little bit of a different situation going on here. We have, I'm going to break this out again, x minus 2, all over x minus 2. All right, now look here. We do have some canceling that's going to happen again here. And then there's some stuff left over. Now here is where I would say there was a hole. Okay, you're only going to have x minus 2 from that numerator still left. So your graph is going to look like the line x minus 2, except there's a hole here. If you were to look at your graph, it'll probably look like that. So I'm going to try to type it like it did from the beginning and then show you what we're talking about here. So, all right, we're going to go up here and we're going to type in x minus 2 all over x minus 2. All right, I'll look at my graph. And again, what you're seeing here is that just a line that looks like the line x minus 2. Now here's the deal. When I get to an x value, skipping, I'm going to go up to calculate and say find. No, go to. And let's look at what the x value at 2 is going to be. Okay. You'll see when I made it go to where x is 2, it's saying undefined. Your graph is not going to show an obvious hole in it necessarily. There might be some graphs that do, but most of them don't actually show it because it is such an infinitely teeny tiny thing because it's just that one specific value. And so there's like a little hole in your graph there where and it's just hard to, they can't show it. So unless they were to program the calculator to put like an empty hole there, that's the only way that they could get that to do that, but they don't. So we're stuck with having to figure it out ourselves. Anyways, there is going to be a hole where x is 2. Otherwise, there's no asymptotes or anything in this one. Not any that we can see, actually. So there could actually be one, but just not obvious ones. And I know that sounds weird. We're going to get to that in a minute. Okay, so let's go ahead and talk about the hole, though, because there's going to be a hole where your x value is 2, okay? I'm going to say, no, based off of that. Hole at x equals 2. So we need to figure out what is that whole coordinate supposed to be because they didn't give me the y value that you're supposed to have. Now you can go on either side of that hole and you can kind of guess. So on the left side of this, it's showing negative 0.4. On the right side of this, it's showing me positive 0.4. So you can probably make a good guess as to what that would be. But if it's harder to see where that hole is, then what I would suggest that you do is I would suggest that you just plug that value. You know that it's at 2 and plug that into this value right there. So if I did 2 minus 2 is going to give you 0. So it's actually at the coordinate 2, 0 for that hole. Okay. But they want limits, right? So we need to talk about limits. Okay. So if I write a hole with limits, we're going to say my limit as x approaches this x value, but we're also going to talk about it approaching from the left, right? As we approach that value from the left, as you approach this value from the left, it's actually getting closer to your y value being 0. And as you approach it from the right, you get closer to a y value of 0. So we've got to make sure that we are being specific. All right, we're going to say that for both ones, but because they are the same thing, then we can actually end up kind of cutting out theirs, and you can make it a little bit more simple and say that the limit as x approaches 2, regardless of if it was from the left or the right, it was approaching the same thing. It was approaching that 0. Okay. All right, we still have a part C, guys. So let's get through that, and then that'll probably be it for this first video, okay? All right. Limit notation, and we have part C. Okay, so on this one, guys, we are going to do the same thing where we kind of see what it is that I can cancel and see if that presents any holes. So what I see right off from the beginning is the x minus 2 is canceled. Now, I don't want to draw on that because that's the notes I'm planning on using in my class, and I don't want to mess them up before we have class. So I'm going to rewrite my h of x function over here we had x squared minus 1, and then we have x minus 2. All of that is over x minus 2. So the x minus 2's are going to cancel. Okay. And that presents me with a whole. So we are going to have a whole where your x value is 2 again. Okay. Now the y value might be a little different this time. So we're going to have to test it and see. Okay. But there is going to be a whole where my x value is 2. In order to tell where that x value or where that y value would end up being, what I can do is I can plug this in. So I'm going to say h of 2, and we're going to just look at this x squared minus 1 because that is what's left after you cancel. That's 4 minus 1 is 3. So my whole is actually at the point 2, 3. Okay. Now, I'm not going to worry about the asymptotes here. If you actually work it all out, we're going to get to in the next video, we're going to get to how you can find some weird asymptotes. For this, if we were to graph it, I don't know that we would see any clear ones because it's a little odd the way that this is. We can look at it and we can decide. I'm just typing it in really quick. I don't know that you'll see them on this. Yeah. All I'm seeing is this guy, and you are going to see those two holes. So there's no obvious asymptotes, although we will end up eventually talking about how you can find some. Okay. Okay. So let's talk about writing this hole as a limit real quick, and then we will be good. So remember, we need to talk about this approaching from, if we are approaching from the left side. So as we approach that x value from the left side, we got to think about the fact that my function h is getting closer to that y value 3. And then the same thing from the left. And because we know that it's going to the same thing on either side, and you can kind of confirm that by looking at your graph, it's not like it splits and goes off to a different location. Okay. Then what we know is that we can kind of cut out the from the left and from the right thing. Just say as it approaches 2. There are some cases where it may not actually do all of that. So that's why we break it apart like this, is sometimes when you approach something from the left or the right, it can be a different outcome. Similar to what we had on the part A. I'm going to go back to that work really quick. On part A, you guys saw that we were able to have over here, when I approached, here it is, 2 from the left, we approached negative infinity. And when we approached 2 from the right, we went towards positive infinity. So they don't always match, right? And that's why we list them out separate like that. And if they happen to match, then like over here on part B, they did happen to match, which means that you can cut out kind of the from the left and from the right part and make it a little bit shorter. Okay. All right, that is it for this first video, part A. Definitely make sure that you watch out for part B, which is going to be what we cover on day 2. Okay.